to algorithms for computing eigenvalues. So it's been a while. So what we have is the QR iteration. So what you do is you choose some orthogonal matrix Q naught, or a unitary matrix really, and then we form our initial matrix in our sequence. Now, a simple choice for Q naught would just be identity. That would definitely work. So, we'll look back to the good part. And then we just begin this iteration. And we take our most recent T matrix and we QR factorize it using either householder flexions or Gibbons rotations, whatever method you want to use. And then we just take these factors and multiply them in reverse order. And this almost always will work eventually at causing, so what happens is TK converges to a quasi-upper triangular form. Now, if A is a real matrix, and it has complex eigenvalues, you will not ever get upper triangular form because everything that's happening here is real arithmetic. But what I mean by quasi-upper triangular is you get 1 by 1 or 2 by 2 diagonal blocks. And if you try this in MATLAB or Octave, you'll see this happen. Where the 1 by 1 blocks correspond to be real eigenvalues, and the 2 by 2 blocks correspond to complex eigenvalues that occur in complex conjugate pairs. Okay. So we have a way of getting eigenvalues, but it's not Miller time yet because we have two big hurdles. One is this is too slow. Each iteration is order n cubed, floating point operations, both for the QR factorization and the matrix multiplication, so that's terrible. And the other big problem is that the convergence is very slow. So too many iterations, each iteration takes too long. So what I'm going to get started on, and we'll see how far we get with it today, is I'm going to fix this problem of each iteration taking too much time. So we're going to speed those up. And then next class, oops, start erasing my line here. Next class we'll look at the other problem of the fact that the convergence is too slow. That can be speeded up. Right now we're looking at order n to the 4th operations altogether to compute eigenvalues, and that's just way too many. Okay. All right. Now, so how to make this process of A equals QR and an override of A being RQ faster? Well, an obvious direction to take is try making A almost upper triangular. Because that way, QR factorization has less work to do, because QR factorization, its job is to zero out all entries below the diagonal. If there aren't as many entries, then there's less work to do. Okay. Now, here's where we have to be careful. So we're going to do a pre-processing stage. Actually, I already have it written into the algorithm. So T naught is equal to, I'll write this way for consistency of my notes. Okay. And for simplicity, you can assume that everything here is real. We're dealing with a real matrix. Okay. And we want that to be almost upper triangular, T naught. Then hopefully, as we carry out iterations, it'll maintain that almost upper triangular structure and eventually converge to something that is upper triangular. So, U transpose, let's try making it a, right? Yeah, it doesn't matter. Making it a product of household reflections. So the idea is A, I start with A, and I apply a household reflection, I'll call it P1, and then I have to apply it on the other side. Remember, we're preserving eigenvalues. Whatever transformation I apply to one side, I must apply its inverse to the other side. But household reflections are their own inverse, so I can have the same thing on both sides. And then apply another, P2, and so forth. And I don't know yet how many transformations I'll need to apply. I'll just call it K. So then I'm accumulating a product of all of these. I'll call this U, and therefore this is U transpose, because each one of these P's is a household reflection that are symmetric and orthogonal. And if you multiply two orthogonal matrices, the product is orthogonal. And from this we get T naught. Okay. Now, so the question now becomes, how to choose these household reflections to make matrix T naught easier to work with as far as computing a QR factorization or performing matrix-matrix multiplication. Now, I'll start with what seems to be the most obvious choice, and you'll see where it goes wrong. Then that'll tell us how to fix it.
Where are you in the notes? Just curious.
What?
Where are you in the notes?
I'm on page 179.
Oh.
In the middle.
Oh, gotcha.
Okay. So let's suppose I let P1 be a household reflection that transforms the first column of A into a multiple of E1. So it's like QR factorization. Zeroes out everything except the first entry. Now, so the idea is P1 times A now has this structure. So if something non-zero, I'm going to be doing a lot of these matrices, so it's important to get used to it now. Where I'm going to use x's to represent non-zero entries. So x's and o's, and obviously the o's are for 0. Okay, so it zeroes out everything in the first column except for the first entry. Now, in order to do that though, P1 has to affect all rows of A in order to achieve this effect. Okay, but now what do I have to do? I have to preserve eigenvalues. So I have to apply P1 on the right now. Well, applying P1 on the left affects all rows. Applying on the right is now going to affect all columns. So, let's see. So now I'm going to be taking linear combinations of these columns, and all my work is undone. Okay, so there's no point in zeroing these things. We had to unzero them, non-zero them, to get our eigenvalues back. So we need to tweak this a little bit. Whatever we want to do, we don't want to affect all rows and therefore have to affect all columns. So if we want to do something to the first column, we have to leave alone the first row. That way, whatever we do when we apply this Hausdorff reflection on the right, it won't touch the first column. It'll preserve our work. So, so here's what we'll do instead.